All right, today we're going to deconstruct a really cool rule in chemistry, one that explains what happens when you mix liquids together. It's called Raoult's law, and honestly, it's the key to understanding the pressure that builds up inside pretty much any solution. So let's get right into it. But before we get into the nitty-gritty, let me ask you something. Have you ever wondered why a sealed bottle of water feels, pressurized, especially if it's been sitting in the sun, but an open glass of water right next to it? Nothing. The answer to that little puzzle is the foundation for everything we're about to talk about. It all comes down to a concept called vapor pressure. Okay, so before we can even begin to tackle how solutions and mixtures behave, we've got to build our foundation. And that foundation is all about understanding vapor pressure itself. Get this, and the rest will totally make sense. So, check this out. It's kind of amazing what a huge difference a simple lid makes. In an open glass, the most energetic molecules on the surface, poof, they just evaporate and escape into the air. Gone. But put a lid on it, and now they're trapped. They evaporate, sure, but they bounce around and eventually condense back into the liquid. After a while, you reach this perfect balance. It's like a dance, where the number of molecules leaving is the same as the number coming back. That's what we call a dynamic equilibrium. And it's in that equilibrium that vapor pressure is born. It is literally the pressure created by all those trapped gas molecules pushing down on the surface of the liquid. So here's the absolute key takeaway. You need a closed container to get that equilibrium. No equilibrium, no vapor pressure. It's as simple as that. Of course, not everything even bothers to create a vapor pressure. We can basically split all substances into two camps. First, you have your volatile substances. Think water, ethanol, benzene, stuff that evaporates easily and definitely creates a vapor pressure. Then you've got the non-volatile stuff, like sugar or salt. You can leave a bowl of salt out for a million years and it's not going anywhere. It produces pretty much zero vapor pressure. And believe me, this distinction is going to be super important in a minute. Okay, with all that groundwork laid, we are finally ready for the main event, Raoult's law. The best way to think about it is as a perfect idealized model. It's designed to predict the vapor pressure of what chemists call an ideal solution. So what does this law actually say? Well, it's actually pretty straightforward. It says that the amount of pressure a single component contributes to the mix, that's its partial pressure, is directly tied to how much of it is actually in the solution. It's pure logic, right? If you have more of component A, its vapor is going to contribute more to the total pressure above the liquid. It makes perfect sense. And here is the math that makes it all work. It might look a little intimidating, but it's not, I promise. PA, the partial pressure of our component, equals P naught A, that's just the vapor pressure of that component when it's completely pure, multiplied by chi A, which is its mole fraction. Now, mole fraction just means what percentage of the molecules in the solution are this component. So if, say, half the molecules in your solution are component A, its mole fraction is 0.5, and its partial pressure will be exactly half of what it would be all by itself. Now, here's the catch. For this law to work perfectly, the solution has to be ideal, which, let's be honest, is pretty rare in the real world. An ideal solution has to follow some really strict rules. The big one is that the forces of attraction between all the molecules have to be pretty much identical. Whether it's molecule A attracting another A, or B attracting B, or even A attracting B, it's all the same. And because of that, two other things happen. When you mix them, no heat is created or absorbed, and the final volume is exactly the sum of what you put in. No shrinking, no expanding. And when you plot this on a graph, an ideal solution looks beautiful. You get these perfect straight lines. See, as the mole fraction of a component goes up, its partial vapor pressure increases in this perfectly predictable linear way. And that top line, that's just the total pressure, which is simply the sum of the two partial pressures below it. It's clean, it's predictable, it's, well, ideal. But reality is almost never that clean. It's often messy, most solutions aren't ideal, the molecules start interacting in weird ways that make them stray from Raoult's perfect model. So let's dive into what happens when these solutions start to misbehave. First up, we've got something called positive deviation. This is what happens when the solution's actual vapor pressure ends up being higher than what Raoult's law told us to expect. You can see it right there on the graph. The lines aren't straight anymore. They kind of bulge upwards, showing us there's more pressure than our ideal model predicted. So why on earth does this happen? It's all about how the molecules feel about each other. In these solutions, the different molecules A and B just don't like each other as much as they liked their own kind. The attraction between them is weaker. And because they're not holding on to each other very tightly, it's way easier for them to just escape and fly off into the vapor phase. More vapor means, you guessed it, higher pressure. And then you've got the flip side, negative deviation. As you can probably guess, this is when the actual vapor pressure is lower than the ideal prediction. And the graph shows exactly that, with these curves that dip down, falling below that nice straight line of our perfect ideal solution. The reason for this is, you guessed it, the exact opposite of what we just saw. This time, the attraction between the different molecules, A and B, is actually stronger than their attraction to their own kind. Maybe they form new hydrogen bonds or something similar. This powerful new attraction holds the molecules much more tightly within the liquid, making it a lot harder for them to escape. Fewer molecules managing to get into the vapor phase means lower vapor pressure. All right, that's a lot of theory. Let's make this real. The best way to see how this law works is to actually use it, so we're going to walk through a quick calculation. This is where it all really starts to click. Okay, here's our problem. We're mixing 0.78 grams of benzene with 0.92 grams of toluene. Our mission, should we choose to accept it, is to figure out the partial pressure from each one, and then, of course, the total vapor pressure of the whole mix. And here's everything we need to solve it, all laid out for us. We've got the mass of each substance, their molar masses, and most importantly, we have the vapor pressure of each liquid when it's pure. Remember, that's our crucial P0 value. The process itself is actually super logical, just a few simple steps. First, we have to convert the grams of each liquid into moles. Easy enough. Step 2, we use those mole counts to figure out the mole fraction for each one. Then, with the mole fractions handy, we just plug them into Raoult's law to find their partial pressures, and for the grand finale, we just add those two partial pressures together. That's it. And when we run through those numbers, we find that the partial pressure of benzene is 200 millimeters of mercury, and for toluene, it's 100. Add them up, and you get a total vapor pressure for our solution of 300 millimeters of mercury. See? The model works beautifully. And that really brings us to a bigger final thought. We've just seen that even a simple mix of two liquids can misbehave and stray from a perfect scientific model. It really makes you think, doesn't it?
Thanks for watching, and don't forget to subscribe our channel.